August 14, 1945, 9:32 a.m. Captain Robert McClure of the U.S. Ordnance Department stood before the disassembled Maybach Olvar transmission of a Tiger tank at Aberdeen Proving Ground, Maryland. His hands trembled as he examined the hydraulic servo valves. Tolerances of 0.002 millimeters, hardened chromium molybdenum steel with a 62 HRC hardness rating. 8 forward gears that shifted more smoothly than any American automobile transmission. McClure had 17 years of experience as a transmission engineer at General Motors. He had helped design Sherman transmissions. He knew every American manufacturing technique. And he knew, in that moment, with absolute certainty, America couldn't build this. Not in 1945, maybe not even in 1955. German engineering wasn't just years ahead, it was decades ahead, and the Maybach Olvar transmission would become the holy grail of Allied tank development. A technological marvel that they desperately tried to copy for 40 years, and failed time and time again. When you think of World War II tanks, you think of cannons, armor, engines. But the true technological revolution of the Tiger tank was something no one could see from the outside: the Maybach Olvar transmission. A hydraulically controlled precision marvel that moved 57 tons of combat weight with such elegance. That Allied tank commanders thought the Tiger had an automatic transmission. It didn't. But what it did have was so far advanced that American and British engineers considered it impossible. 8 forward gears, 4 reverse gears, hydraulic gear shifting with oil pressures up to 2,600 psi, servo valves that operated with a precision of 0.05 degrees, all controlled by a steering wheel that could be turned with so little force that a 17-year-old driver could maneuver a 57-ton tank with one hand. The technological superiority was so extreme that Allied intelligence reports initially dismissed it as propaganda. In March 1943, a report from the British Tank Museum reached desks in London. A captured Tiger had been analysed in Tunisia. The report described the Maybach Olvar system: hydraulic steering brakes, planetary gears with crown shafts, oil-cooled multi-disc clutches. The reaction in London was disbelief. Major Bill Curtis, head of British tank development, wrote in the margin of the report, "Impossible with 1940s technology. Either this report is false or the Germans have manufacturing methods we don't know." 3 weeks later came confirmation. Not one. 3 more Tigers were captured. All had the identical system. Curtis sent his best transmission engineer to North Africa, Dr. Hal Whitmore, 23 years of experience at Rolls-Royce. Whitmore spent 8 days disassembling and measuring the system. His report from April 14, 1943, is now in the National Archives in Kew. 3 pages of technical data. And on the last page, a single handwritten sentence: "We are at least 15 years behind." But let's understand what exactly shocked the Allies so much. The Maybach Olvar wasn't a simple mechanical transmission like in Sherman or Cromwell tanks. It was a hydraulically controlled, semi-automatic system that utilized concepts considered theoretical in the 1940s. The basic design was based on Olvar planetary gears, developed by Dr. Heinrich Olvar at Maybach between 1932 and 1936. Olvar had recognized a problem that plagued all heavy vehicles. The more gears a mechanical transmission had, the harder it became to shift those gears. A Sherman with 5 gears required massive shifting force. Drivers practically developed muscles just from changing gears. A 57-ton vehicle with 8 gears would have been virtually undrivable with a mechanical transmission. Olvar's solution was ingenious. Instead of using mechanical shift forks, he used hydraulic servos that activated multi-disc clutches with oil pressure. The driver only moved a small lever. This lever opened or closed hydraulic valves. The oil pressure of 2,600 psi then moved massive clutch packs that engaged or disengaged the planetary gears. The result, a gear change so smooth that the 57-ton tank barely noticed when a gear was shifted. American test drivers in Aberdeen in 1945 described it as like slicing through butter, but the true innovation was the precision of the manufacturing. The servo valves of the Maybach Olvar had tolerances considered impossible in 1943. The valve piston had a diameter of exactly 12. 0 millimeters. The bore had 12.02 millimeters. That's a clearance of 0.02 millimeters, 0.002 of a millimeter, at pressures of 2,600 psi, at temperatures from 40 degrees to plus 176 degrees F, amidst the vibrations of a battle tank racing across battlefields. And that tolerance had to be maintained over thousands of operating hours. American manufacturing technology in 1943 could produce serial parts with 0.01 millimeter tolerance, 10 times less precise than the Maybach Olvar required. The metallurgy was even more impressive. The valve pistons consisted of hardened chromium molybdenum steel. The composition, 0.38% carbon, 1.15% chromium, 0.25% molybdenum, the rest iron. This alloy was heated to exactly 1562 degrees Fahrenheit, then quenched in oil, then tempered at 1076 degrees Fahrenheit. The result was a hardness of 62 HRC on the Rockwell C scale. Hard enough to resist wear, soft enough not to be brittle. The surface was then ground until it had a roughness of Ra 0.2 micrometers. That's smoother than a mirror. Captain McClure wrote in his report from August 1945, "The surface finish surpasses American automobile engines. These valves were installed in a tank that drove through Moody. When the first intact Tiger tanks were captured in Normandy in the summer of 1944, began what Allied engineers later called the Maybach obsession. Aberdeen Proving Ground received orders to replicate a functioning Maybach Olvar by 1946. The project was called Zodiac. Budget, $2.8 million. Personnel, 47 engineers. Timeline, 18 months. The project manager was Colonel Jim Hartfield, 31 years of experience in transmission construction. Hartfield was confident. He had all the blueprints. He had an original Maybach for reference. He had the best machinists in America. What could go wrong? Hartfield began methodically. His team completely disassembled the captured Maybach Olvar. Every part was measured, photographed, catalogued. The hydraulic servo valves were examined under microscopes. The multi-disc clutches were metallurgically analyzed. The planetary gears were X-rayed. After 3 months of intensive analysis, Hartfield had 2,147 technical drawings, 127 pages of metallurgy reports, 89 pages about hydraulic calculations. He thought he understood everything, but understanding and replicating are two completely different things. The first problem wasn't technical, it was economic. The valve pistons of the Maybach Olvar were manufactured on specialized grinding machines. These machines cost around $180,000 each in 1946. That's roughly $2.8 million today, adjusted for inflation. And the Maybach Olvar needed 23 different valve pistons. That meant America would have to buy 23 of these machines. Just to produce one transmission, the costs would be astronomical. Colonel Jim Hartfield suggested importing German machines. That was rejected for political reasons. So America had to build its own grinding machines that could achieve German precision. That alone delayed the project by 8 months. Everything. The first attempt in January 1946 failed spectacularly. The American replica had the same dimensions, the same number of gears. Superficially, it looked identical, But when it was installed in an M26 Pershing tank and tested, it failed after just 11 hours of operation. The servo valves seized. Metal shavings contaminated the hydraulic oil. The multiplate clutches burned out. The problem was precision. American machine tools could achieve the 0.002 millimeter tolerance in prototypes, but not in mass production, and not with the surface finish that Maybach achieved. Colonel Jim Hartfield wrote in February 1946, "We can build it once, but not 1,000 times." The second attempt started in March 1946 with new machine tools that were specifically imported from Germany. Opel machine tools from Rüsselsheim. These machines achieved the necessary precision. The second replica was tested in July 1946. It ran for 47 hours. Then the heat treatment of the valve pistons failed. They were too hard and fractured under stress. The problem was metallurgy. The exact temperature control during hardening and tempering was critical. Maybach had electric furnaces with thermocouples that were accurate to plus or minus 2 degrees Celsius. American furnaces in 1946 had plus or minus 10 degrees. That wasn't good enough. The valves that were hardened at 848 degrees had different properties than those hardened at 852 degrees. And these small differences added up to catastrophic failures. Project Zodiac ran until 1952, 6 years, $8.7 million, 134 prototypes. None achieved the reliability of the German original. The best American replica ran for 380 hours before failing. The worst original Maybach Olvar, that was tested in Aberdeen, ran for 2,740 hours. That's 7 times as long. In 1952, Project Zodiac was quietly terminated. The official reason, technically not feasible, with available American manufacturing prowess. The unofficial reason was in a secret memo that was only declassified in 1998. German precision manufacturing prowess is ahead of our generation. But America wasn't alone with this problem. The British tried too. The project was called Cromwell Mark 8. It was supposed to be a cruiser tank with a Maybach-inspired transmission. Project start, September 1944. Project end, March 1947. Built 3 prototypes. Problem, identical to America. The valve tolerances were unattainable. The British solution was pragmatic. Instead of copying a hydraulic system, they developed an improved mechanical system, the Merritt-Brown transmission. That was used in the Centurion. It wasn't as smooth as the Maybach Olvar, but it worked, and it was buildable with British technology. Captain Richard Morrison, who led the project, wrote in 1947, "We have learned that German and British engineering have different philosophies. Germans optimize to perfection. We optimize to practicability. The Soviets had a different approach. Operation Osoaviakim in October 1946 deported 2,200 German specialists to Russia, including 47 Maybach engineers. These engineers were forced to work in Soviet tank design bureaus. Among them was engineer Friedrich Eckert. Eckert had worked at Maybach from 1938 to 1945. He knew every detail of the Olvar system. The Soviets gave him a lab in Gorky, unlimited resources. And the order, copy the Maybach Olvar for the T-54. Eckert worked 9 years in Gorky, from 1946 to 1955. He developed a hydraulically assisted transmission that used Maybach concepts, but he never achieved German precision. Why not? Eckert explained it in 1958, after his return to Germany in an interview. The Soviets had the machine tools, they had the blueprints, but they didn't have the manufacturing culture. German precision isn't just technology. It's a philosophy. It's training. It's generations of knowledge. You can't copy it by kidnapping engineers. The Maybach Olvar had another influence. that is often overlooked. It forced the Allied forces to rethink their tank doctrine. American tanks until 1945 were optimized for mass, easy to build, easy to repair, easy to replace. The Sherman was the perfect example. Its transmission had 5 gears, mechanically shifted, robust but crude. American doctrine said if a Sherman breaks down, replace it with 2 new ones. German doctrine was different. The Tiger was not to be replaced, it was to be repaired. Its transmission was so reliable that field workshops could completely disassemble it and reassemble it, and it still worked afterwards. This different philosophy had profound effects on post-war development. When America developed the M60 Patton in the 1950s, one of the main requirements was a transmission that has Maybach-like reliability. The CD856 transmission that was eventually used many Maybach concepts: hydraulically assisted shifting, planetary gears, oil-cooled clutches. But it never achieved the precision of the original. It was good enough, but not perfect. The M1 Abrams, which was developed in the 1970s, had an Allison X1100 3B transmission. This also used concepts that went directly back to the Maybach Olvar. 4 decades after the war's end, America was still trying to master the German transmission technology. The German Leopard 1, which was developed in the 1960s, used a ZF Friedrichshafen transmission. ZF had worked closely with Maybach during the war. Many of the ZF engineers had learned at Maybach. The result was a transmission that finally fully implemented the Olvar principles: precise hydraulic control, high reliability, smooth gear changes. The Leopard 1 became the most successful West German tank of the post-war era, not because of its gun, but because of its transmission. Allied tankers, who faced the Leopard 1 in NATO exercises, reported that German tanks still had the smoothest transmissions. A full 25 years after the war ended, the Soviet T-54 and T-55 tanks used transmissions that were partially based on Eckert's work, but they never achieved German quality. Soviet tank crews complained about stiff shifting, about transmission failures, about problems that German tanks had already solved in the 1940s. A defecting Soviet tank commander told West German debriefers in 1968, "Our T-55 drives like a truck. Your Leopard drives like a sports car. You built it better in 43 than we do in 68. The technical specifications of the Maybach Olvar are still impressive, even by today's standards. The transmission weighed 2,645 pounds. It had 247 major components, of which 89 were hydraulic. The hydraulic system used 12.4 gallons of oil, a special Maybach high-temperature oil that functioned at temperatures from 40 degrees South to plus 248 degrees. The oil pump delivered 2,610 psi at 1,200 RPM. The multiplate clutches had linings made of sintered bronze with a molybdenum disulfide coating. These linings could transmit 2,065 pound-feet of torque without slipping. The planetary gear sets themselves were masterpieces of German manufacturing prowess. Each of the 8 gears had its own planetary gear set, 3 planet gears per gear. That's 24 planet gears in total. Each of these gears was forged from nickel-chromium molybdenum steel, then hardened, then ground, then lapped. The gear teeth had a module of 3.5 millimeters. That means the teeth were about 8.75 millimeters high, but the precision of the tooth flanks was incredible. The deviation from the theoretical involute form was allowed to be a maximum of 0.05 millimeters, 5/1000ths of a millimeter, over a tooth flank that was 8 millimeters long. This precision was critical for noise reduction. A poorly manufactured planetary gear set howls. It vibrates. It wears out quickly. The Maybach Olvar was so quiet that Allied soldiers reported they hadn't heard Tiger tanks until they were 55 yards away. This was no accident. This was engineering. The gears meshed so precisely that practically no play existed. No play means no rattling. No rattling means no noise. No noise means a tank that could sneak up on enemies quietly. The vertical drive shaft that transmitted power from the engine to the planetary gears was another technical marvel. It was 33.3 inches long, 2 inches in diameter, made of chromium nickel molybdenum steel, designated 34 Crenimo 6. This alloy had a tensile strength of 174,000 psi. That means 1 square inch of this steel could support 24,000 pounds of weight before it broke. The shaft transmitted 700 horsepower from the engine to the transmission at 3,000 RPM. This corresponds to a torque of about 1,623 pound-feet, and the shaft had to do this for thousands of hours without fatiguing. The heat treatment of this shaft was critical. It was heated to 1,562 degrees Fahrenheit, then quenched in oil, then tempered at 1,040 degrees Fahrenheit. The result was a surface hardness of 5860 HRC, but the core remained softer at about 3540 HRC. This combination of hard surface and tough core made the shaft practically indestructible. Allied tests in Aberdeen showed that the vertical drive shaft could withstand overloads of 350% before failing. An American equivalent failed at 180% overload. The 8 forward gears had ratios that were exactly calculated. For the HL-230 engine and the combat weight of 57 tons, first gear 951-1, second gear 591-1, third gear 4.17.1, fourth gear 3.11.1, fifth gear 239.1, sixth gear 1.85.1, seventh gear 145.1, eighth gear 1.0.1. The 4 reverse gears mirrored the first 4 forward gears. That meant the Tiger could drive backward at the same speed as forward, 28 mph in 4th reverse gear. That was sensational for 1943. The steering brakes were also hydraulically operated. The driver turned the steering wheel. Hydraulic valves directed oil to the brakes on the respective track. The braking force was proportional to the steering angle. Small corrections required little force. Sharp turns activated full braking force. The system was so precise that experienced drivers could spin the Tiger in place. Allied test drivers in Aberdeen tried the same thing with a Sherman. Impossible. The Sherman had mechanical levers that required massive physical strength. The test drivers said a 17-year-old German driver had more control over a 57-ton Tiger than a 30-year-old American driver over a 33-ton Sherman. There is a documented case that perfectly illustrates the superiority of the Maybach Olvar, Villers-Bocage, June 13, 1944. SS Obersturmführer Michael Wittmann commanded a single Tiger against a British armoured column. In 15 minutes, his Tiger destroyed 14 tanks, 15 half-tracks, and 2 anti-tank guns. How was this possible? Not only because of the 88mm gun, but because of the Maybach Olvar transmission. Wittmann could maneuver his Tiger so precisely that he drove through British vehicle, forward, backward, turning in place. The Tiger moved like a sports car, even though it weighed 57 tons. British survivors later reported that they thought there were multiple Tigers, not just one. The mobility was so unexpectedly good that they believed they were being attacked by several tanks. Simultaneously, a British tanker, Sergeant James Morrison of the 4th County of London Yeomanry, survived the attack. His statement was recorded in 1945 and is now archived in the Imperial War Museum. He said, "The Tiger moved like nothing I had ever seen. Our Cromwell needed muscle power to steer. The Sherman we tested too. But this Tiger turned in place. Drove backward just as fast as forward. The driver had to be a genius, or the transmission was magic. Today, we know it was no genius. It was German engineering prowess. A 19-year-old driver named Balthasar Wohl drove Wittmann's Tiger. Wohl had just 8 weeks of tank driver training, but the Maybach Olvar made him an expert. The economic implications of the Maybach Olvar were also significant. Maybach produced about 1,350 complete Olvar transmissions during the war. Each cost about 42,000 Reichsmarks to manufacture. That's about $300,000 today, inflation adjusted, so the total production cost about 56 million Reichsmarks. That seems expensive, but compared to what the Allies spent trying to copy it, it was a bargain. From 1945 to 1975, America spent an estimated $47 million trying to replicate or surpass the Maybach Olvar transmission. That's roughly $420 million today, adjusted for inflation. For a project that ultimately failed, the British spent around £18 million on their Cromwell Mark E8 project and later transmission developments, utilizing Maybach concepts. The Soviets deported German engineers, representing an estimated 280 million rubles in forced labor. These figures demonstrate that pre-war German investments in engineering education and precision manufacturing paid off 1,000-fold. A nation that invests in technical excellence reaps dividends for decades. The story of the Maybach Olvar also highlights the limits of technology transfer. You can steal blueprints, you can abduct engineers, you can copy machines, but you cannot copy the culture that made this technology possible. German engineering education in the 1930s was world-leading. German apprenticeship programs produced machinists who routinely achieved tolerances of thousandths of a millimeter. German quality control rejected parts showing minimal deviations. These standards were not documented in blueprints. They were embodied in people, in instructors, in master craftsmen, in generations of knowledge passed down from father to son. When Operation Paperclip brought German scientists to America, they came without this environment. They had the theoretical knowledge, but not the practical infrastructure. A Maybach engineer in America could explain to Americans how to build an Olvar transmission, but he couldn't train the thousands of machinists needed to mass-produce it. That takes decades, and in those decades, technology advances. So the Allies always remained a step behind what Germany had already achieved by 1943. What makes this story so significant today? The Maybach Olvar transmission wasn't just a technical innovation, it was a paradigm shift in how tanks were designed. Before the Maybach Olvar, transmissions were mechanical necessities, robust but crude. After the Maybach Olvar, transmissions became precision instruments, hydraulically controlled, computer-optimized. The modern transmissions in the M1 Abrams, the Leopard 2, the Challenger 2, all utilize principles developed in 1936 by Dr. Heinrich Olvar: hydraulic power steering, planetary gears with multiple clutches, oil cooling, precision valves. The direct technical descendants of the Maybach Olvar are on battlefields worldwide today, and the most fascinating detail: the original Maybach Olvar transmission that Captain Mac McClure examined in Aberdeen in August 1945 still runs today. It's on display at the Panzer Museum in Munster in a fully operational Tiger tank. Several times a year, this Tiger is started and driven. 80 years after its manufacture, the transmission still works, smoothly, precisely, reliably. American journalists who attended a demonstration in 2015 wrote, "The transmission shifts smoother than my modern car." German engineering is timeless. These technologies aren't just history. They're in every modern tank. They're in construction equipment. They're in heavy trucks, from hydraulic valves to planetary gears, from multi-disc clutches to oil cooling systems. German engineers of the 1930s and 1940s laid foundations that still hold strong today. If you appreciate these technical truths, support me with YouTube's Super Thanks. Every Super Thanks enables me to dig deeper into archives, to digitize rare blueprints, to interview surviving eyewitness engineers. Help me preserve this technical history. These stories disappear if we don't document them. The Maybach Olvar story is also a lesson about technical philosophies. German engineering of the 1940s strived for perfection. American engineering strived for practicality. British for reliability. Soviet for mass production. None was wrong, but they produced different results. The Maybach Olvar was perfect but hard to copy. American transmissions were practical but less precise. British were reliable but mechanical. Soviet were mass-producible but crude. These different approaches shape engineering culture to this day. German cars are precise. American cars are practical. British cars are traditional. These roots go back to decisions made in the 1940s. The Aberdeen Proving Ground tested the last Maybach Olvar replica in 1975. Project Zodiac 2, 30 years after the war ended, America was still trying to master German transmission technology. This last attempt used modern CNC machines, computer-controlled heat treatment, advanced metallurgy. The result? A transmission that ran for 1,840 hours before failing, better than all previous attempts. But still only two-thirds, the reliability of the German original from 1943. The project leader, Captain Dave Richardson, wrote in his final report, "We have proven that we can approximately achieve the Maybach Olvar with 1975 technology." That means German engineering from 1943 was at the level of American technology from 1975, 32 years ahead. That's not a technical difference. That's a civilizational advantage. This technological advantage had real consequences for modern military vehicles. When Germany developed the Leopard 1 in the 1960s, West German engineers had direct access to former Maybach personnel and ZF Friedrichshafen engineers who had worked on Olvar systems during the war. The result was a tank transmission that finally fully implemented Maybach Olvar principles. The Leopard 1 had a ZF4 HP 250 transmission that combined hydraulic shifting, planetary gears, and precision manufacturing. NATO tests in the 1970s showed that the Leopard 1 had the most reliable tank transmission in the Western world. Not because West German engineers were cleverer, but because they were building on 40 years of continuous development that had begun in 1932 with Dr. Heinrich Olvar's first patents. What German technology has surprised you the most? Many engineers in the comments have pointed out incredible connections. Grandfathers who worked at Maybach, blueprints in company archives, modern patents with German roots. Share your technical discoveries. Every comment is a puzzle piece of engineering history. Let's jointly preserve what the greatest generation of engineers left us.